All righty. Let's see if we can't finish up chapter one here. So where we left off last time is we were looking at the radial distribution function. So the radial distribution function, as you can see, is going to tell us the probability of finding an electron at some distance r from the nucleus. Okay, now we know that orbitals, of course, are going to take different shapes. So if you see here, here's your 2pz orbital. You can see that's two lobes with the node in the middle. Down here, you see your various s orbitals. However, the radial distribution function is going to consider everything spherically out from the nucleus of the atom. The shapes of the orbitals are going to be, well, we'll talk about that in a minute. First thing I want to cover is we're looking at a concept called the probability density. So the probability, you can get there's a slight difference. Probability density, as you can think of as the larger the probability density gets at a certain value of r, the more likely you are to find an electron there. Now, we could integrate the probability density, and what we would end up with is the probability from 0 to 1, which would give us a percentage of finding an electron at a certain radius. So they're very similar, but very slightly different. So keep that in mind. The density is the higher the density, the more likely you are to find the electron at a specific radius. And even though we're looking at these radii spherically, the electrons, for if they're in a p orbital, will still be within these regions where you see the lobes of the p orbital. They'll just be so far out from the nucleus. Now, I want to cover some math here you may not have seen before. If you look at this, you see that the wave function squared is what it's called psi star psi. Now, the star is what is called the complex conjugate. Okay. So that means, so let's say we have part of our wave function that we found earlier. The complex conjugate, all it's going to do is it's going to take everything that's imaginary and change the sign of it. So really not that bad. Every time you see a star, you're just going to change the sign on the imaginary parts. And as you can see, our psi star psi for our radial distribution is going to end up being the radial part of our wave function, complex conjugate times itself. So, of course, as I said, the probability is when you'll get the actual probability when you sum or integrate over the probability density. And I wanted to show you a little bit of notation here. So what you see here on the left, this is called Dirac notation. And so it's called the bracket notation. So bracket. And whenever you see this, this represents an integral. And so in this case, you see the bra, and so the bra facing to the left is going to be your complex conjugate. The vector facing to the right is going to be your standard wave function. And so at some point, and this represents the integral you see here. At some point, for example, in quantum mechanics, you may see psi. It's another representation where you see the Hamiltonian operator. And this would be the same integral with your complex conjugate, your Hamiltonian operator multiplied in. So like that. So this is just called Dirac notation. And it's a quicker way. It's a kind of, sometimes it's a cleaner way to write your integrals. So I would just start getting used to that because you'll see this kind of notation all over quantum mechanics. Now, we remember that our wave function has both a radial and an angular portion. Now, this radial distribution function is not going to take into account the angular portion. So these spherical harmonics, these are this the angular portion there is what's going to really dictate the shape of your orbital, whereas your radial portion is going to dictate how far out from the nucleus you are. That's why we're still able to work with the radial distribution function uh, in spherical space. Okay, so here we have part of a sphere, and you can see this part of the sphere is in the uh, first octant of a XYZ axis, because of course that would be your X direction there. Now, when we want to actually integrate over the whole of a sphere, uh, the first thing we're going to do is we're only going to do the two-dimensional integral because we're only worried about the sphere at a specific radius. And then we'll get that sphere again at another radius and so on and so forth. So we're only worried basically like a spherical shell. And so that's why we have these little portions, dA. So it's an infinitesimally small portion of the surface of that sphere. Now, what you see here, so first off, you can start to get a grasp of how these things are working. So theta is measured down from the z-axis, phi is measured from the x-axis, and then we have our radius r. And so as you can see here, we have d theta. Now here we have d phi, but what we end up looking at is, let's look at this right triangle right here. Okay. So to really figure out that infinitesimally small area, we see that we're looking at two. It's think of a rectangle. You multiply width times height, two-dimensional rectangle. And so what we want is we want the arc lengths on each side. So we'll call that arc length 1, and that's going to be my r d theta. And then arc length 2, that is going to be, so your r sine of theta, that distance out from the z-axis, and then it's going to be d phi. So the reason our arc lengths look like this is because the arc length formula is going to be your radius multiplied by the angle that you move through. And so the way you can think about this is, the reason, for example, we use the r sine of theta, is this sphere is going to be measured as tiny circles, well, maybe not even tiny, that go, that's a horrible drawing, but it's best I could do. And so we have a circle at that part of the sphere, and we're going to essentially integrate over all those little circles all the way down. And so just start comparing these, the rd theta and the r sine of theta d phi, to the arc length formula, and you'll see how this works itself out. But what that means is that our area, your area is going to be S1 times S2. So remember, think of this like a two-dimensional rectangle. That's going to be length times width. And so then that's going to equal r d theta. And then we're going to have r sine of theta d phi. And so our area element is going to end up becoming r squared sine of theta d theta d phi. Okay, so the radial distribution function, we're going to call it G, And what we're going to do is we're going to integrate over each one of these spheres. So here's the thing. Well, let me back up a little bit. So let's take our definition of our integral. Okay. All right. Now, when we integrate this, as you remember, in this case, our wave function is going to be our radial portion. That's going to be r squared r, which we get from here. And then it's going to be dA, because we're just worried about the probability density at a specific radius, and so in that radius then will then produce spherical surfaces. So the dA, all those dAs, when you integrate over them, so the since we're staying at a specific radius, the r squared value becomes a constant. We're not integrating over r, so at least over this portion of the wave function. However, well, we're not integrating over r period. Then we have our dA, we're going to replace r squared sine of theta, d theta, d phi. Now we're going to go to our radial distribution function. A very classical way to represent this is you have your g. Now we're not integrating over r. So let's go ahead and we have the radial portion of our wave function. R squared comes out. Now, you notice how we have an integral over theta and an integral over phi. So this is probably your first look at a double integral. I'm going to go ahead and put the limits on here so I can write it out neatly. We'll talk about this. So we're just going to integrate over these angular portions. Okay. So let's talk about the limits. Now, the first integral, you notice how you have sine of theta d theta. So your inside integral, the 0 to pi, that's going to be over your theta. Okay. That means you're going to end up integrating from the positive z-axis 180 degrees down to the negative z-axis, or pi radians. Okay. Then your outside integral, your integral over phi, to turn that into a sphere, you're going to take and integrate it all the way around a full 2 pi radians. And so those two integrations together will end up giving you an entire spherical surface. So a little review here. This radial wave function, even though it's done spherically, as your orbitals get bigger and bigger and bigger, or higher and higher energy, this is still going to help you figure out exactly where in each orbital the electron is most likely to be, because again, your orbitals are not going to really change shape all that much. Let's review for a minute. If you remember here, you notice how, let's say you have your 2p, 3p. So even though you've gone up in energy and the orbitals are getting bigger, they're not changing shape all that much. So you're still going to be able to radially locate the electron pretty efficiently. Okay, now let's look at solving this integral. Okay, so the first thing we want to do is we're going to take this first integral here, okay? So if I take 0 to pi, sine of theta d theta, and really what you're doing is you're doing each integral and then multiplying them together. Okay, well, your integral, so your integrals and derivatives of sine and cosine. So your integral of sine is negative cosine. Integral of negative cosine is negative sine. Integral of negative sine is positive cosine. Integral of positive cosine is positive sine. You just keep going around in this circle. Okay, so this one, positive sign becomes negative cosine of theta, and we're going to evaluate from 0 to pi. Now, remember, evaluation is a difference, okay? So this means I'm going to have a negative cosine of pi minus a negative cosine of 0. Okay, well, cosine of pi, that's a negative, -1, minus, and cosine of 0 is 1, so negative cosine of 0 is -1. And when we add this together, we get 2. So that integral itself just comes out to be the value 2. And so now I'm able to pull that out, and I'll show you what I have left. Now my radial distribution function is I've already pulled out the r's. So now I have 2 r squared r squared, and I have my 0 to 2 pi integral over d phi. Now, of course, we know an integral over a differential is the best integral we can get, because all that's the integral of d phi just comes out to be phi integrated at the limits. So this will be 2 r squared r squared phi evaluated from 0 to 2 pi. And that means 2 r squared. And then we're going to have 2 pi minus 0. And so by the time we're done, you notice that our radial distribution function is going to equal 4 pi r squared multiplied by the probability density of the radial part of our hydrogen wave function. So this is what you see in the textbook. I just showed you how we get there and how we think about it. And to reiterate what I was saying about this d phi, let's say, for example, we had an integral just of dx. Whenever you integrate a differential, you just get that value back. So that's x. And for all of you math majors out there, I know x plus c, but this is more physics, okay? So yes, physicists, we do a number of things that make mathematicians very, very mad. So just go with it. All righty. And so to give you an idea of the radial distribution function, look at some of these distributions here. Notice how the 1s orbital has a maximum distribution very near the radius. Your 2s, now let's go back up for a second. Do you remember here how you have these nodes and 1 node, 2 nodes? That's what you're showing here on the graph. Every time you hit a 0 line, that's a node. So then your 2s has a little bit of electron density near the radius, but then it's going to have most of its electron density out further. And then so then again with the 3s, you have node, and most of the electron density is going to be further out. So you can start to see your most likely the most likely location that you're going to find an electron. Alrighty. Let's look at an exercise here. Okay. So here, will the plot of the radio part of the wave function for a 1s atomic orbital of helium plus be identical to that of the H atom, given the following hydrogen 1s wave function? Okay, well, you remember helium plus is a hydrogen-like species because it has one electron orbiting a nucleus. Okay, that's hydrogen-like. Now let's think about this. These two are not going to be identical. So let's do part A. And let's just do well, not instead of X and Y. We're going to do the radial part of the wave function versus the radius. And for hydrogen, what we're going to get is something very close to that. Versus for helium, yeah, needs to shoot down further here. So you notice how the, and this will be hydrogen, this will be helium. Now you notice how the hydrogen has a much smoother slope. You get more electron density uh, at a larger radius versus the helium pulls most of its electron density in right to the nucleus. Well, the reason those aren't going to be the same is remember the nucleus of the helium atom has a larger positive charge. So it's going to pull the electron density in closer to the nucleus of the helium plus ion. But what about part B? Approximate representation of the radial distribution function for both of these. This is supposed to be helium plus. Okay, so again, on this axis, we're going to have the distribution function. And on this axis, we'll have the radius. Okay. And so, of course, for helium plus, we know that it's larger positive charge on the nucleus, going to give us a function that looks a lot like this. And you can model these off of graphs you see in the chapter versus the hydrogen. Going to look something like this. Whereas we get much more of a spread of the electron density for the hydrogen than we do for the helium. Okay, orbital energies of a hydrogen-like species. Now, the equation the book gives you is this negative kz squared over n squared. Now, I'm not crazy that they're using k there because I want you to pay attention. We have a k and then we have a k sub e. Okay, so that k is just a constant. The k sub e that's going to be your Coulombic constant, the 1 over 4 pi epsilon 0. Now, since we're talking about hydrogen-like species, also notice the Z there. That's going to be your atomic number. So for like helium plus, Z would be 2 because you're going to have 2 protons in that nucleus. Okay, so let's start looking at how we find these energies based off the Bohr model. Okay, so we're bringing into account here a couple of things. So first off, in the Bohr model, the kinetic energy of a moving electron, 1/2 mass of the electron, velocity squared. The potential energy of the electron. Now, this is going to be a Coulombic potential. So Coulombic potential is going to be your negative Coulomb constant. Now, Okay, let's look at it. Let's look at potential. Okay, so very close to your electrostatic force, only it's 1/r. In this case, if we have a proton in the nucleus and an electron, both of these are going to have the base charge of E. So that means this potential energy is going to be, so we need to include the atomic number, and then E times E is E squared over your radius R. That's your potential energy of an electron. And of course, we know that the total energy of a system, kinetic plus potential energy. So we're going to get the kinetic energy, KE Z E squared over R. So the Bohr model shows us that our Coulombic force, our force of attraction. So let's go ahead and write that. How much space do I give myself? Oh, I have some room. Okay. So remember our Coulombic force, so our electric force, that's going to be our Coulomb constant, C, and of course, Q1, Q2 over R squared. And of course, both of those charges are going to be the base charge E, E Z E squared over R squared. So there's our Coulombic electric force. We also know that centripetal force, mass of your electron, V squared over R squared. And since your Coulombic force, your electrostatic force, is centripetal force, but this is going to give us MEV squared over R squared equals KE ZE squared over R squared. And so now we're going to start solving this. We're going to, let's see. So we're going to solve this for MEV squared, because you notice here, MEV squared. Okay. And the M sub E is the mass of an electron. So when I multiply 2 through by R, and so that the math works out properly, I need to back up a second. Let's correct centripetal force. It's not over R squared, it's just over R. That'll correct it. Okay, now I'm going to multiply through by R, and we get KE CE squared over R. Now I'm going to substitute this into my total energy equation. Which will now give me 1/2 KE ZE squared over R minus E ZE squared over R. Well, we know this is going to give us KE ZE squared over 2R minus, and then we can call this fraction on the right 2 KE ZE squared over 2R. And so our energy is going to come out to be a negative. So this is going to be a 1 minus 2, so it's a negative KE ZE squared over 2R. Okay, now, when you look up the Bohr model, what you're going to find is a couple of equations for angular momentum of a moving electron. Okay, so particle moving in its orbit. We label angular momentum as L. This is going to be mass, you just say mass for your electron, V, R, velocity times radius. Quantized, quantized angular momentum, L is going to be N, H bar, where of course N is your principal quantum number. So in the Bohr model, we now have mass of your electron V times R equals NH bar. And we're going to solve for V. And that's going to give us NH bar over MER. And of course, remember that H bar is an abbreviation of Planck's constant. It's Planck's constant over 2 pi. We just started using a different letter for it because it shows up so much, it makes things easier. Now, what we're going to do is we're going to go back up and we're going to pull out this equation. Okay. So what I'm going to have is ME B squared AEZ E squared over R. And I'm going to substitute in my equation for V. ME in H bar over MER squared AEZ E squared over R. All right. So this is going to give us mass of the electron N squared H bar squared over ME squared R squared. Well, the ME is going to cancel out one of the MEs. So we're going to get N squared H bar squared over MER squared. And again, that equals our KE Z E squared over R. All right. So then I'm going to multiply through by the R squared. So that's going to give me R squared KE Z E squared over R equals N squared H bar squared over ME. And so what I'm going to end up solving for R. I'll cancel out one of the R's, so that'll cancel. And when I solve for R, my R with respect to the principal quantum number N is going to be N squared h bar squared over MEK. And that's our, again, our the K there is our Planck's constant with the sub E on it. Z E squared. Now, what we've done here, this is kind of fun. This is actually your Bohr radius. So a lot of you have read textbooks and you've heard about the Bohr radius. Another way to represent this is A sub 0. So this is your Bohr radius. Now, but what we're going to want to do with this is we want to go back to our total energy equation. E, that's your negative KE Z E squared over 2. And then there's your Bohr radius in the denominator. So let's pull that out times 1 over the Bohr radius. And then we're just going to take that Bohr radius and flip it upside down. Okay, so mass of your electron, Planck's constant, not Planck, Coulombic constant, Z E squared, where Z is your atomic number, E is the base charge. So the charge of a proton, charge of an electron, over N squared, principal quantum number, H bar squared, Planck's constant over 2 pi. And when we solve this, we end up with the energy of our electron at an energy level, principal quantum number N. We get negative mass of our electron, KE squared, Z squared, E to the 4th, over 2 N squared H bar squared. Okay, so to make this look like the textbook, let's go ahead and pull out. We're just going to call this is your energy at a principal quantum number of N. I'm going to pull out the negative Z squared over N squared. Then what's left is your ME, the Coulombic constant, E to the 4th, over 2 H bar squared. And if you look at the equation from the textbook, let's go all the way back up. Right here, Z squared over N squared, you see that? We go back down here. This whole value right here is what the textbook called K. Now, this is going to have a couple of values. So K is going to be about 13.6 electron volts, or something you might be more used to, 1.312 times 10 to the 4th kilojoules per mole. And for those of you who have worked with the Rydberg equation before, this also equals our HC, the Rydberg constant, Planck's constant times the speed of light. So a lot of you have used the equation RHC 1 over N final squared minus 1 over N initial squared. Well, this is the RHC. So the Bohr model does have its weaknesses and its strengths. So the real weakness of it is it postulates that every orbital at a specific value of N is going to be degenerate. So like your 3s, 3p, 3d orbitals are all the same energy. Well, we know that that's not quite true. Like your 3p will be higher in energy than 3s, your 3d will be higher in energy than your 3p and your 3s. So this is a weakness of the Bohr model. But the Bohr model does show us that the value of n uh, increases orbital energy levels. Hang on. But for higher values of n, orbital energy levels are going to come closer and closer and closer together, which of course is a physical reality. So if you think about n equals 1 here, n equals 2 here, 3 here, 4 here, and so on and so forth until they're virtually on top of each other. The Bohr model does accurately predict that. Okay, so determine the energy of the 1s orbital of the helium plus ion and compare it with that of the 1s orbital of the H atom. Okay, so let's do the energy of our hydrogen, negative z squared over n squared times k. So for hydrogen, z equals 1. So that's a negative 1 squared over n equals 1 squared. And then we're going to do 1.312 times 10 to the third kilojoules per mole. And this is going to give us the 1s orbital energy of negative 1.312 times 10 to the third kilojoules per mole. And also pay attention to how these energies are negative. So in quantum chemistry, a negative energy is a bound state. So this is an electron that's still bound to its nucleus. It hasn't reached ionization energy. It hasn't reached escape energy. So now let's look at the energy of the H plus ion. Z squared over n squared times k. For helium, Z is 2, and it's going to be over 1 squared. 1.312 and 10 to the third kilojoules per mole. And this should come out to be about a negative 5.248 and it's 10 to the third kilojoules per mole. Well, with that number being more negative, you notice that the helium nucleus binds that one electron much, much tighter than the hydrogen nucleus does, which makes sense because there is two protons providing electrostatic attraction in the helium nucleus versus one proton in the hydrogen nucleus. So the electron is going to be bound quite a bit tighter, which if we go back to those graphs we looked at earlier, explains why most of the electron density on the helium nucleus is much, much closer to the nucleus, whereas the hydrogen can spread the electron density out a little more. Okay, let's go on with our final quantum number, the magnetic quantum number, m sub s. So we know that electrons can be labeled with spins of a plus 1/2 or a minus 1/2. And so because they're 1/2 spin particles, they're known as fermions. These particles obey the Pauli exclusion principle. Your whole number particles, like your bosons, do not obey the Pauli exclusion principle. And bosons are going to be like your photon, your Higgs boson, so on and so forth. Think of your bosons as your force carriers in nature. So, like without the photon, there would be no electric or magnetic force. And so you see that as the spin of the electron changes, the magnetic field of the electron will flip its poles. And so we know for each orbital, it now is going to be governed by three quantum numbers, n, l, and m sub l. So this spin angular momentum quantum number. So n is your principal quantum number, l is your angular momentum quantum number, m sub l is your magnetic quantum number. And now your electron, each electron is going to be governed by four quantum numbers, n, l, m sub l, and now your spin angular momentum quantum number, m sub s. All right, many electron atoms. So now we're getting up to the point where we can't really solve the wave function analytically, because once we get to a nucleus and two electrons, well, we're already back to the three body problem. But we do have ways of approximating the wave functions for many electron atoms. One of them here you see here is called density functional theory, or DFT. So density functional theory, instead of dealing with each electron individually, is going to treat the electrons as an electric potential cloud, and then it's going to calculate the response of each electron to that cloud, and then it will have corrections in there so you're not double counting or having an electron responding to itself, which was one of the first errors of DFT. But since then, people have been working on functionals that will weed that out. Now, in the Bohr model, of course, we saw that the weakness was that all orbitals at the same energy, at the same value of n, are going to be degenerate. But, for example, we actually know that let's say we have your 2s orbital. We know that 2p is actually going to be a little bit higher in energy than that. -1, 0, +1, 2p. And so, of course, if you wanted quantum numbers, your 2s, n equals 2, l equals 0, m sub l equals 0. And for your 2p, n equals 2, l equals 1, and m sub l, going from minus l to plus l, -1, 0, +1. And again, well, this is the n equals 2 level. We need to get to n equals 3 to get our first d orbitals, but you get the idea. The s will be lower in energy than the p, which will be lower in energy than the d. Now, the reason for this energy difference is when we start looking at ground state electron configurations. So all these spectra that we've been looking at are caused by atoms getting hit with radiation, electrons jumping up in energy to another set of orbitals, and then falling back down. When they de-excite, they release photons in that for each element is going to have these very characteristic spectra. We can use some basic quantum mechanics to calculate the energy between various values of n, but the SPD orbital differences, we're taking into account electron repulsion, electron core attraction, and electron shielding, which is a new topic for you. Here, I want to give you an example of a ground state configuration for nitrogen. We'll just look at the valence electrons. So your 2s electrons will be there. Your 2p electrons, 1, 2, 3. And when this ground state configuration is hit with radiation, you get a promotion. The 2s, those are very stable, those are paired, but one of these 2p orbitals, or 2p electrons, will then have its electron bumped up to the 3s level, and that'll be your excited state. Now, penetration and shielding. Okay, so for electron penetration, I'm going to scroll back up here for a second because I want us to again take into account. Where is it? Here. I want us to take into account these s orbitals. You notice the nodes between 2s and 1s, 2s, and 3s. Okay. Now, that doesn't necessarily mean, look at the 3s. It doesn't necessarily mean that all 3s electronic energy is bound to that outer orbital. You have those nodes, which are areas of zero electronic density because those are quantumly forbidden levels. But if you notice here, notice that your 1s electron, electronic orbital, has most of its electron density near the nucleus. Well, we would expect that. But then again, if we look at your 2s orbital, we notice that, yeah, most of its density, electron energy is going to be further out than the 1s orbital. However, again, you have the node right there, but it still is going to have some electronic energy within the 1s region. And again, for the 2p, you still, like 2p is your first level of p, you only see the one arc, but it's going to have some electron density within both the 1s and 2s region. So there is going to be electronic energy penetration into the lower energy shells. Given the fact that there are nodes where it's quantumly forbidden for electrons to be, and so you'll have zero electron probability density at the nodes. Now, the whole concept of shielding is, you see here we have the nucleus with Z is our number of protons, and you notice how outer electrons are repulsed by inner electrons. Those inner electrons form kind of a shield that reduces the effective nuclear charge the outer electrons see. So if your nucleus is like lithium, where Z equals 3, those outer electrons are not going to feel the electronic attraction of a full 3 protons. The inner electrons, due to the repulsion, are going to lessen that proton electron attraction for the outer electrons. And so what we can do is we have our effective nuclear charge is going to be the atomic number minus your shielding constant. And there are rules, Slater's rules, for estimating the shielding constant. So for example, you're going to write out the electronic configuration of the element being examined. The electrons in group higher than the one being considered, they don't matter. Then you have rules for your NS, NP orbitals. And so when they say a group, so like let's say you have 2s electrons and 2p electrons. All of those electrons within 2s and 2p are part of a group and will contribute your 0.35 to each other if they're in that same group. For every n minus 1, you get s equals 0.85, and for every n minus 2, you get s equals 1. If you're looking at nd and nf orbitals, again, let's say you had 4d and 4f. Those are all going to be a group. Everything within 4d and 4f is going to contribute 0.35, and each of the electrons in lower groups are going to contribute 1. So it's going to be your n minus 1 and on down. Okay, so let's use Slater's rules to show that the Z effective is 5.2 for a 2p electron of fluorine. Okay, well, fluorine, that's going to be 1s2, 2s2, 2p5. Now we look at the periodic table. Z equals 9. Okay, so we're looking at one of the 2p electrons, okay? So that's one of these. Now, we have 4 other 2p electrons, and then we have 2s electrons. So that's going to give us let's just do them one at a time. Okay, so you have 4. Whatever 2p electron you're looking at, there's still 4 left in the 2p level. So let's just say the shielding constant for this is going to contribute those 4 electrons times 0.35. This will give us 1.4. Okay, because those are, again, 2p, those are all in the same group. Now, what about your 2s electrons? Well, those are still part of the n equals 2, the 2s 2p group. So that'll be S2 times 0.35. And that's going to give us 0.7. And then you have two 2s electrons. So, or two 1s electrons. So that's going to be your n minus 1 electrons. That'll give us a contribute shielding of those two electrons times 0.85. It's going to be 1.7. Your total shielding constant you add those three together and you're going to get 3.8. Okay, so then your effective nuclear charge should be a positive 9 from the protons. Well, let's go ahead and say well, that's our Z minus S. That should be a full positive 9 from the 9 protons in the nucleus, but we have to subtract off the 3.8 shielding constant for an effective nuclear charge of a positive 5.2. So that's all of the proton charge that those each 2p electron is going to feel, not the full 9 of the protons in the nucleus. Okay, so here we go. For Slater's rules, let's estimate the effective nuclear charge for a 4s and a 3d electron in a V atom. V is vanadium. Then, using this answer, explain why the valence configuration on the ground state of vanadium plus is likely to be 4s1 3d3 rather than 4s2 3d2. Okay. So first, let's figure out vanadium's electronic structure. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3, and the atomic number is 23. Okay. The 4s electron. Okay, so for my 4s4p group, I only have 4s electrons. If I'm looking at one of them, I have one other 4s electron. So my shielding constant will be that one electron times 0.35 equals 0.35. Okay. Well, now we go to n minus 1, which is 3. So if I count those up, I have 11 n minus 1 electrons. So that's going to give me a shielding constant of 11 times 0.85 equals 9.35. And then everything for n minus 2 and below, that's going to give me 6, 2, and 2. So I have 10 n minus 2 electrons. It's going to give me a shielding constant of 10 times 1.0. And so my total S value, I add all those together, I get an S of 19.7. So then I say that the effective is the atomic number minus S. That's 23 minus 19.7. So that's going to give me a value of 3.30. So that means that a 4s electron on vanadium is only going to feel about 3.3 protons instead of all 23 protons in the nucleus. Now, notice here how we did have d electrons and we did have different rules for d. In this case, we were examining an electron in a 4s orbital. So we use the first set of rules for the 4s for the NS-NP groups. If we were examining one of the 3D electrons, we would completely, well, we'll do that next. So you'll see how this works. Okay, so for a 3D electron, okay, so let's look here. So 4 n equals 4 is above n equals 3, so we're not even going to consider those electrons. Those aren't going to contribute to shielding because they're further out than the 3D electrons. Okay, so I have 3D electrons. That means I'm looking at one of them. I have 2 more. So I don't have any 3F. So the only electrons in the 3D 3F group are going to be those 3 and the 3D electrons. Of course, we can't have 3F. F doesn't start until n equals 4. But that means I have 2 electrons there. So for my 3D electrons, my shielding constant is going to be the 2 electrons that are left that I'm not looking at times 0.35. That's going to be 0.7. Now, so for the ND, NF groups, we now do all of the electrons in lower groups. Okay, that means that I'm even going to consider the 3s, the 3 and the 3p electrons, as those are going to be lower in energy than the 3D. Because your ND, NF group will be higher in energy than NS, NP. So that means I have a total of 18 electrons in lower groups. All right, so that's going to be a shielding contribution of 18 times 1.0. My total shielding constant now is going to be 0.7 times 18.0, or 18.7. So my effective nuclear charge is going to be 23 minus 18.7 equals 4.3. So now the 3D electrons are going to fill 4.3 of the protons in the nucleus versus the 3.3 protons of the 4s electrons. So the way we can say, well, the reason that when vanadium becomes vanadium plus, we strip off one of the 4s electrons versus one of the 3D electrons is the effective nuclear charge for the 4s electrons is lower than the effective nuclear charge of the 3D electrons. So the 3D electrons are actually held tighter, meaning that your primary valence shell is going to be your 4s, and electrons are going to be stripped from there first, being the highest energy shell on the atom. So that's why your plus 1 ion is likely to be a 4s1 3d3 versus a 4s2 3d2. It has to do with the size of the effective nuclear charge, 3.3 versus 4.3. Okay. So ionization energy. So that's the energy needed to remove an electron from an atom. And of course, these ionization energies can go one after the other after the other. They're usually measured in delta U, which is internal energy at 0 Kelvin, or for thermochemical calculations, enthalpy, your delta H at 298 Kelvin. So for example, we know that magnesium wants to become isoelectronic with its nearest noble gas. So that's going to be magnesium 2 plus. We know from its place on the periodic table that it's a common charge ion. It's going to become 2 plus, which means it's going to have 2 ionization energies. So if we look here, Your ionization energies are done in gas phase. So you have your magnesium. Your first ionization goes to magnesium plus, and it is going to have a delta H of 737.7 kilojoules per mole. And then your second ionization it's going to have a delta H of 1450.7 kilojoules per mole. So keep in mind, as your for each individual ionization, these enthalpies are going to go up quite a bit, and that's because again, every electron you remove is going to reveal more positive charge from the nucleus of the atom, and is going to hold every other electron much tighter. Here you have a nice graph that shows you the ionization energies of your various groups on the periodic table. Notice how your noble gases are much higher than other elements in the group or in the period. Yeah, this isn't groups, this is periods, whatever. Um, that's because your noble gases, of course, have a full outer shell of electrons. They're very, very stable. But let's take a look at how we can understand ionization energies. We can actually understand them through screening. So if you see we have sodium here and neon way up here, well, let's look at neon for a second. Now, if neon was to be ionized, one of those two p electrons would have to come off. So so if we look at just one of those two p electrons, and then we say, well, how many 2s 2p electrons do we have left? That'll be 7. So that'll be what? S equals those 7 remaining electrons, 0.35 equals 2.45. Then you have your 2 electrons from your n-1 level. Those 2 electrons in the 1s times 0.85 equals 1.7, a total S value of 4.15. So an effective nuclear charge on neon, that's going to be, your Z is 10 minus 4.15. That's going to equal, your 2p electrons in neon are going to see 5.85 of those protons in the nucleus. Versus, see how much lower the ionization energy of sodium is? So let's look at that. We have neon. Now let's do sodium. 1s2, 2s2, 2p6, 3s1. Now we know if we look at the periodic table, sodium must become isoelectronic with neon. So that means it's going to lose that 3s electron. Let's see. So if we're looking at that 3s electron, we have no other electrons in the 3s 3p group, so we have to instantly go to the n-1. We have 8 electrons from the n-1 level. That's going to be 8 and 0.85. That'll give us 6.8. And then we have 2 electrons from n-2. It's going to be an S of 2 times 1.0. A total S value of 8.8. So our Z for sodium is 11 minus 8, the 8.8 shielding constant equals 2.2. So you notice how much lower the effective nuclear charge is for the sodium than the neon. This is a very good reason for why the ionization energy for sodium is so much lower than the neon noble gas. So you can start to understand these ionization energies through electron shielding or electron screening, however you want to say it. Okay, so stability of electrons in their various orbitals can be understood through a new idea that you've probably not seen before called quantum exchange. So electrons in degenerate orbitals that have the same spin, they can, I wouldn't really say delocalize, but it's a lot like that. They can just start swapping places with each other. And the more they swap places with each other, the more electrons you have undergoing exchange, the more energy, the lower the energy of the electron configuration goes. And of course, we know lower energy means more stability. So for example, let's say we have at our 3p level, two electrons with the same spin versus two electrons with opposite spins. Those two electrons with the same spin become more stable due to exchange energy. Now, I've shown you what I've shown you over here. First off, that K, that integral there, that is going to be your exchange integral. Notice how the wave function, you have wave function I, wave function J, the 1 and 2, it's electron 1, electron 2. And then notice how those will swap the wave functions on the other side. That's to represent the exchange. And then, of course, your operator in the middle of this is going to be your Coulombic potential. So your integral here would look like this for the most part. Nope, nope, I didn't get enough size in there. Forget that. We'll come back to Dirac notation at a later time. But anyway, you notice that you have your two orbitals, an orbital for each electron, and then you have the psi star psi, the psi squared of each electron. And then notice that the electrons switch places on each side of the operator. So that represents the exchange. And then what this does is when you put that, when you use that operator, the inside of the integral, what it produces is the exchange energy once you solve the integral, which is essentially going to give you your -1/2 sum of all of your summing together all of your exchange integrals, and it gives you a negative n minus 1 over 2 multiplied by the exchange integral. Okay, so that n in the n minus 1 over 2, that is going to be the total number of electrons with parallel spins. So you take all, so here n would equal 2, n equals 0 for there. So the more spins you have with that are parallel or in the same direction, the higher your value for n is going to go. And so this exchange energy is really important to stabilizing atoms and molecules. Okay, so we want to also talk about electron affinity, which is very close to ionization energy. It's kind of the reverse. It's how much does a specific atom want to take on another electron. And again, here you see we have our electron affinities, but notice at the very top are halogens. Because we remember, for example, that group 17 or 7a, based off the periodic table you're looking at, those want to take on another electron to become isoelectronic with the noble gas right next to them. So for example, chlorine plus an electron becomes the chloride ion. And we're all familiar with this. But of course, we see that the delta H is going to be a negative 349 kilojoules per mole, meaning that this is an exothermic reaction. And so as chlorine takes on that electron and expels heat, we know that it's becoming much more stable. So electron affinity, not too difficult, very close, pretty much the opposite of your ionization energy, but still an important topic to start wrapping your mind around. Okay, well, that's going to really wrap up chapter 1. So the next time we meet in class, we will work on chapter 2. All righty, and then after chapter 2, we'll be done with our kind of our deeper dive into general chemistry. And then we'll start with one of our primary inorganic topics, which is going to be molecular symmetry and point groups. All right, well, I will talk to you later.